Hi guys, I would like to do a little review of this week's lectures. This covers class on January 27th and yesterday, January 29th. Last lecture we talked a lot about molecular orbital theory, probably more than you ever wanted to know. Don't worry, you probably won't see it again until OChem 2. Um, but we got to talk about some hybridization stuff and how this molecular orbital theory feeds into hybridization. So if you recall, last time we talked about oxygen and how it overlaps, and side-to-side pi orbital over p orbital overlap to give you pi orbitals and sigma star and all that stuff. But now we want to start talking about carbon, right? So carbon's electronic configuration, if you remember from Gen Chem, is 1s2, 2s2, 2p2. So if we draw that out in our little cutesy diagrams, we get 1s2, 2s2, 2px, 2py, 2pz. Those are our three p suborbitals. And we have two electrons, so we do that. So this was our atomic configuration, right? But when carbon makes bonds, it doesn't really use this configuration because essentially it's not fair. If you recall from Gen Chem, it's better to have a completely full orbital, meaning you have a full octet, which we don't have enough electrons for here, a completely empty orbital, which we have too many electrons for, or a completely half-filled orbital. So this is not particularly good, energetically speaking, that is. What carbon does to solve this problem is a thing called hybridization. So what it's going to do is take its valence shell, right, that's the most external shell that has electrons in it, and it's going to physically shuffle them around such that it no longer has distinct s and px and py and pz orbitals, but rather it hybridizes, that's what we call this, so that instead of having distinct p and s orbitals, it smooshes them together to give you four sp3 hybrid orbitals. So we get four orbitals, each of which is called an sp3 orbital. How many electrons do we have total? 1, 2, 3, 4. We populate them according to, I believe it's Hund's rule, it says one electron each shell. And a half-filled orbital is better than this weird combination of not half-filled orbitals. So this is energetically a better thing to do. Right? We call this the sp3 hybridization scheme, so we usually just refer to it as sp3. And why do we call it that? Because in order to make each one of these orbitals, we used one element of the s orbital, and we used one element of the, or all three of the p orbitals. So each one uses one of the p orbitals, so all of the s and all of the p are occupied in making this orbital. What effect does this have on the geometry? Well, if you remember, an s orbital is a sphere, and a p orbital is kind of like a little figure eight lobe, something like that. There are three of them, three orientations in space. This would be our s, and this is px, py, and pz. If you smush them together physically in space, now you're basically biasing the shape of the p orbital such that it's blending with the s orbital, and you're getting a hybrid orbital that looks something like this. So that will be one of the sp3, that will be another sp3, that will be another sp3, and I'm trying to draw them relatively correct orientations in space, although I doubt you'll see the three-dimensionality to it. Right? So each one of these orbitals is called an sp3 hybrid orbital, and of course it can only have two electrons, just like the same rule for orbitals. It turns out that if you take these four different orbitals and you attach them to the carbon, the orientation in space that they occupy is that of a tetrahedral molecule. So hopefully you remember the shapes from Gen Chem. Right? We draw it this way with the wedge, meaning something's coming out at us, the dash, something's going back away from us. And typically, we only draw the big part of the orbital. If you notice, each orbital has like a little tail here. We typically just don't draw that just because it gets in the way and kind of makes the image look a little clunky. The bond angle between these orbitals then is the same for all four of them because they're all the exact same as each other. And it's 109.5 degrees if it was a perfect tetrahedron. And in the case of methane, where I have a bunch of hydrogens attached, it is. Okay, so that's one of the hybridization schemes of carbon called sp3. The take-home message for it is that it's tetrahedral. Tetrahedral, that's important to remember. The bond angle is 109.5, important to remember. And the way that I kind of recognize that something is sp3 hybridized, you have all single bonds. That's a nice, easy way to remember What's the hybridization? Oh, it only has single bonds, therefore it must be sp3 hybridized. And if it's carbon with a full octet, it has to have 4 single bonds. One electron goes here, one electron here, one here, one here. That's 4. That's why it has sp3 tetrahedral orientation. But that's not the only thing you can do, right? So I had before my sp3 hybridization scheme. If I take my 2s orbital and my p orbitals, and I mix them up a little bit differently. Instead of taking all 3 p orbitals, so 2p, 2p, and 2p, right? Instead of taking all 3 p orbitals and mixing with the s, what if I only take 2 of them? Well, it turns out what I end up getting then is 3 orbitals that are what we call sp2 hybridized, sp2, sp2, sp2. So I've used one of the p's, I use another of the p's, hence the p2 part, and I use the s, hence the s part. Well, what happens to this extra p orbital? Since I haven't used it, it remains kind of by itself as a p. These sp2 orbitals then look very similar in shape, albeit a little bit different, to the sp3 hybrid orbitals. And so if I have a carbon, it'll look something like this. sp2 orbital, sp2 orbital, and sp2 orbital. All 3 of these orbitals will exist in the same plane, and so the molecule will be the shape that we called, oops, not molecule, trigonal planar. Right? All 3 of these molecules exist in the same plane, i.e. these 1, 2, 3, and 4. Okay. These 3 orbitals want to get as far away from each other as they can because electrons repel each other, and in order to do that, they orient themselves in space such that they're trigonal planar. What does that mean as to the geometry, the orientation in space? What is the bond angle between these? Well, if you have an equilateral triangle, it would be 120 degrees. That's not the end of the story, because we still have this extra p orbital to deal with. Where does that p orbital go? Well, it can't go in the plane because these sp2 orbitals are occupying that space. So it exists perpendicular or orthogonal to that plane, right? This would be our unoccupied p orbital. What is the angle between the p orbital and any of the sp2 orbitals then? Like I just said, it's orthogonal, so it has to be 90 degrees. And that's very important for bonding, because when carbon makes a bond with an sp2 hybrid orbital, it says, here's my sp2 orbital, hybrid orbital. Someone make a bond with me. Oh, I'm a carbon, I'll make a bond with you. I'm an sp2 hybrid orbital as well. Hey, that's good. And we have orbitals here and here, and he has orbitals here and here. This would be our sigma bond that we talked about earlier. But it still has this unoccupied p orbital, and if they come together in phase, right, we'll assume these come together in phase as well, we can not only get the sigma bond, the sp2 orbital overlap, but we can also get the favorable orbital overlap of the p to p side to side interaction. And what we said last time is side to side p interaction, right, gives you a pi bond. The way we typically represent that is with the double bond. One of these is the sigma bond, the other is the pi. Okay? So this is what we mean, the structure over here on the right that I'm coloring. This is what we mean when we draw something like this. 120 degree bond angle right here, and unfortunately there's not really a good way to represent three-dimensional pi bond with that type of drawing. Simple way to remember, trigonal planar, 120 degrees, and a double bond. So if it has a double bond, to be more specific, if it has one double bond and it's a carbon, then it'll be sp2 hybridized. Okay, so that's good. We took all 3 p orbitals, smushed them together to generate sp3. We took 2 of the p orbitals, smushed them together to make sp2. And what do you think's next? You're right. You can take just one of the p orbitals, smush them together to make sp. So you got this to start with. If I just take one of these and one of these, smush them together, I get 2 orbitals. So both of which are sp hybridized. So sp and sp. Again, they're similar shape and structure to the sp3 and the sp2. A little bit different, a little smaller, a little tighter. I think they're a little bit more squat. But general similar structure. There are 2 p orbitals that are unaccounted for now. What happens to them? Well, they just get left alone as p orbitals. Total number of electrons in, 4. So total number of electrons out has to be 4. So they're the same. What happens to our other 2 p orbitals? What happens to our other p orbitals, of which there are 2 of them? One of them exists above and below the plane of the SP. The other one exists in front of and behind. So this would be a p orbital, and this would be a p orbital. The bond angle between SP and SP is linear, right? You have two groups. You want to put them as far away from each other in space as you can. That would be 180 degrees. The orientation between the SP orbital and the p orbital, orthogonal, 90 degrees. And the p orbital and the other p orbital, also orthogonal, 90 degrees. So you can think of it as px, py, and SP's make up the PZ line then. So if carbon is making a bond with another carbon, it says, hey, I have an SP orbital, someone bond with me. And then another carbon says, I'm a carbon, I'll be your friend. We'll make an SP bond. You have this other bond sticking out the other side that can do something. Sticking out the other side that can do something. That's good. Now we have the p orbitals. If they come together to have favorable orbital overlap, right? When they bond, we get carbon. And I'm just going to draw it as a stick right now just to clarify the drawing a little bit because it's going to get messy. And a pi system that exists above and below the plane of the molecule, and the phase remains the same, right? That would be our pi bond, pi, and this one would be our sigma, okay? We should have no problems with that, but there's also one more p orbital. They can come together in phase and say, hey, let's do a triple bond, that's really cool. Yeah, alright, triple bond. So now these orbitals will overlap with each other, and so you get a pi bond that exists in front of the image. So I'm going to try and draw this. Let's see, go like that, try like that. So it occludes a little bit from our point of view the lower lobe of the other p orbital, and then you have a p orbital in the back, kind of like that. Hopefully that looks nice and three-dimensional to you. I never claimed to be an artiste. Alright, hopefully you see. And then we have an an SP orbital sticking out here, an SP orbital sticking out here. And the way we normally draw that in the line angle formula looks like that. We have two pi bonds, one of which is this one, the other one which is that one. And then we have a sigma bond, which is this guy in the middle. And then this is an SP hybrid orbital, that is an SP hybrid orbital. So an easy way to think about it is SP hybridized, 180 degrees orientation in space, right? This whole thing is linear. 180 degrees, linear, and essentially triple bond. There is P-L-E, I can spell. Triple, I don't know how to spell, whatever, no, triple, T-R-I-P-L-E, that looks weird, whatever. There is one other orientation that you can have to get SP hybridization. It's unlikely you'll see it, but I'll throw it in here just for completion. You could technically have two double bonds, right? So this carbon would also be SP hybridized, but in this particular example, this guy would be SP2 hybridized, and that guy would be SP2 hybridized. So a very standard test question that I often ask is, here's a molecule, tell me the hybridization of the atoms that I'm pointing at, and I'll just point at a bunch of random ones. Or I'll point at a bond and say, tell me which orbitals are responsible for making that bond. And if it's like this, I'll say this one is sigma, what is this one? And you have to say it's pi that is composed of p and p, or it's a sigma that's composed of sp and sp2, or something like that, right? Since this guy is sp hybridized, his bond comes from the sp orbital. Since this guy's sp2 hybridized, his bond comes from the sp2 orbital. Very standard test question. So you want to make sure you understand your hybridization. All you really need to look for is bonds. All single bond, sp3. Double bond, sp2. Triple bond, sp. That's simple. Cool, let's move on. I'm getting bored of this hybridization stuff. Right, let's talk about isomerism for a little bit. So I talked about isomerism. In class we talked about what isomers are, and I gave you a big blank chart that we're going to fill in later. But for now, we're just going to talk about the most simple, or what I think is the most simple of isomers, which is constitutional isomers. Not the isomers written by Ben Franklin, but isomers that are made up differently. Right, and the example I used in class, if you were in class, was I used my amazing artistic depiction of a car. So here's a car, in case you're unsure what it was. All cars need steering wheels, and they need wheels. And I said, okay, here's a car. A car is one form of the way that you could take the parts that make up a car and put it together. So this would be one version, but I could take the steering wheel off, and I can stick it somewhere else on the car, and I would still have all the same parts, but I just have them in a different orientation in space, right? I take the steering wheel and I stick it on the hood. Doesn't make much sense, but you can do it, right? Or I could take the wheels off. I'll just do one more example. I could take the wheels off the car, and I could put the wheels on. No, don't do that. I didn't drag my pen. Unnecessary, computer. Right, so I take the car, and I take the wheels off. What are you doing? This software is frustrating me. Okay. I put the wheels on the roof. Not a good place for them. Car's not going to go very far, but you could do that. And at the same time, I'll put the steering wheel on the back end, right? I've used the same parts. I used body and wheels and steering wheel the whole time, but I just connected it up differently, right? Each one of these would be a constitutional isomer of each other, right? So this would be a constitutional isomer, constitutional isomer, constitutional isomer, right? So a constitutional isomer, or more generally, an isomer are different compounds, and we'll talk about how they can be different later. Different compounds with the same molecular formula. Right? So my molecular formula here would be body, steering wheel, and tires, and that's it, right? 3 different things, and I could put them together in all different combinations. Same thing is true with molecules, right? So I think the example I used in class was pentane. Right? Pentane is C5H12. Right? But there's different ways I could draw C5H12. I can draw it this way, which is called N-pentane. If you were paying attention last time when we did our nomenclature stuff, right? You'll know where that name comes from. Pent because there's 5 carbons, ane because it's an alkane, meaning only carbons and hydrogens. But if I chop off this methyl group and I move it over, I could draw this. This is also C5H12, right? But it's different than this one. Why? This has 5 carbons that are directly in a row. This one has 4 carbons in a row with a methyl group, a branch, at carbon 2. Right? And then there's one more way I could draw a pentane. 1, 2, 3, 4, 5. And of course I drew 1 carbon too many, because that's why I like to do this early in the morning. 5 carbons, 1, 2, 3, 4, 5. 2,2-dimethyl propane, technically speaking, but it's also C5H12, right? So we'd say that each one of these is an isomer of each other. Because they're physically put together differently, they're called structural isomers or constitutional isomers, meaning they're constituted differently. And I think the example I gave, or I asked you guys, use C8H18, and I said draw all the constitutional isomers of that. Very standard type of quiz or test question. I'll give you some molecular formula and you have to draw some number of isomers. Very simple stuff. You want to get good at knowing the structural isomers because later on we're going to spend a whole chapter on isomerism, and there's a lot more and a lot more complex things you can do with it. So I'm just going to move on from the isomerism or from the structural isomerism like that and mention stereoisomers. Stereoisomers. All right. Stereoisomers are a little bit different. They're isomers, just like before, hence the name. But the difference is that they're isomers that differ in their orientation in space, or specifically in how their atoms are oriented in space. And it matters, because 3-dimensional orientation in real life can affect what the electrons can or can't do because of where they're at, right? A lot of people can't touch their elbow to their ear because your arm's 3-dimensional orientation doesn't allow you to do that. So let's take a look at a very simple example, and like I said in chapter 5 we're going to spend a lot more time talking about stereoisomers. Right, if I take a carbon, what's the hybridization of this carbon again? What's the hybridization of that carbon? Hopefully we recognize it has a double bond, so it's sp2 hybridized. Right? And so I have this molecule here, right? This is 2-butene. Don't worry about nomenclature just yet. And I draw a molecule that looks like this. Are these the same as each other? No, because here I have one methyl group that is on one side of the double bond, on the top side as it's drawn on the piece of paper, and the other methyl group is on the bottom side. Those are different from each other. Here I have one methyl group on the top side and the other methyl group on the top side, right? So what we call these are geometric isomers, or sometimes also called, and I prefer this terminology actually, cis-trans isomers. Later on when we learn about alkenes, we'll learn that this is called the trans alkene, and this is called the cis alkene. Don't worry about that for now. Again, like I said, we'll get to it later. Okay, so those are cis-trans isomers. They're one type of stereoisomers, but as we'll see later on, there's a whole other can of worms that we can open up when we get to stereoisomerism. Alright, so that's all I'm going to say about Chapter 2. I did mention intermolecular forces very quickly in lecture, but I covered it in my Gen Chem review way back, so hopefully there won't be too much more to say about it. So I want to move on to Chapter 3, which is molecular formulas, nomenclature, big one, structure and conformations, Newman projections, cycloalkanes, and everyone's favorite, chairs and boats. Alright, so this first one is molecular formulas. Right, if I give you C4H10, I can say, draw some structural isomers of C4H10. You would start by saying, okay, I have 4 carbons, so I'll chain them all together. I'll make sure I have the right number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm good. Is there another structural isomer I could draw? Sure. Instead of drawing 4 carbons in a chain, I'll draw 3 carbons in a chain, and that extra carbon I'll put in the middle. Looks good to me, right? That is also C4H10. They are 2 structural isomers of butane. What if I gave you C4H8? Now you say, well, I need 10 hydrogens to be an alkane, so this 8 means I don't have full saturation, meaning not every carbon has the maximum amount of hydrogens possible. So I have to have what we call an element of unsaturation. An element of unsaturation is either a double bond or a ring structure. Okay? You don't necessarily know which one it is. There could be different ones. So let's draw a couple structural isomers of C4H8. I could take the 4 carbons, put them in a chain, but now I have to get rid of 2 hydrogens because now I have too many. So I can do that by inserting a double bond. And I chose to put the double bond at the end of the chain, but I could just very easily put a double bond in the center of the chain, or I could draw the geometric isomer of that in the center of the chain. Hopefully you're seeing the picture. Or I could also draw the ring structure 2, 4, 6, 8, which will give you another isomer of C4H8. Okay. Do the same thing with C5H10. I could say, well, 1, 2, 3, 4, 5, 2, 4, 6, 8, 10 hydrogens. Okay, that makes sense. Or I could draw the straight chain. That's 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 2 hydrogens too many. I'll give it a double bond. And then I'll move the double bond along the chain, and I'll move it there. And then if I move it here, I get the same thing because I can flip it over. So I can draw the geometric isomer of that. And you can play games like that. Right? There's probably a couple more you can do if you're clever. Doesn't matter. Okay. The take-home message is that in order to have an alkane, which is what we're studying here in Chapter 3, in order to have an alkane, you need to have 2n plus 2 number of hydrogens, where n is the number of carbons. Right? So for example, if I give you a chain, doesn't matter how long it is, we'll say 2, 4, 6, 8 carbons long. 8 times 2 is 16, 16 plus 2 is 18, and therefore I should have 18 hydrogens in the alkane. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and that's true. This is a true statement. It means you have an alkane. If you want to determine if you have an alkene or not, then you just use the 2n plus 2 rule the same way. So suppose I said how many degrees of unsaturation are present in, we'll use the same example, C8H16. You say, well, it should be 8 times 2, 16 plus 2 is 18. That's how many I'm supposed to have. How many do I actually have? Oh, I have 16. So I subtract how many I actually have, or excuse me, how many I should have, and how many I actually have, and says 2 are missing. Well, every time you make a double bond, or every time you make a ring, in order to bond those 2 carbons together, each carbon involved in that activity has to lose a hydrogen. So this carbon has lost a hydrogen, this carbon has lost a hydrogen, and so for every 1 degree of unsaturation, you lose 2 hydrogens. And so what we do is we divide it by 2. That will tell us we have 1 degree of unsaturation. If I had C10H18, for example, say 10 times 2 is 20 plus 2 is equal to 22. That's how many I should have in a perfect world where I have an alkane. Actually, I have 18. That leaves 4. 4 divided by 2 means I have 2 degrees of unsaturation, which means either I have 2 double bonds, a double bond in a ring, or a triple bond. Any combination would make that equal 2 degrees of unsaturation. And if you're clever, or if you're a very hard worker, you want to try and draw all the structural isomers of C10H18, H18. It would be great practice, although it might take you a little while. But go ahead and try it. Not saying don't. Okay, so that's it with the structural isomer stuff. 2n plus 2 rule. I want to get to nomenclature next. Nomenclature. Nomenclature is really important in organic chemistry, right? Essentially, it's a systematic way to give every molecule a name and every name to correspond to exactly one molecule, right? So there's a set of rules that we use to name organic molecules. First thing we do is we find the longest chain. Since we're just doing alkanes right now, I'm not going to worry about the more complex structures. We have to add to these nomenclature rules as the structures get more complex. But for now, we're just going to work with the simple case. Find the longest chain. Then we have to number the chain so that the first substituent you encounter is the lowest number. Okay, that's important. Then we have to name the groups attached and specify their position. So I say this is at this position, this is at that position, etc. And then lastly, if we have multiple substituents, we put them in order alphabetically. So if multiple, which is often the case, alphabetize, put them together alphabetically. And if you have one substituent, I don't know, how would I say this? If you have a group that shows up more than once, such as a methyl group showing up multiple times, then you use the phrase di, tri, tetra for 4, tetra, penta for 5, etc., etc. Okay, so let's do a simple example. I give you this structure and say, tell me the name of this. You count the longest chain. Say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, either way I get 5. If I count the other way, 1, 2, 3, that obviously doesn't help. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the longest chain I can get is 5. What is the prefix that I ask you to memorize for a 5 carbon unit? The prefix is pent. Since we're only dealing with alkanes, molecules that have carbons and hydrogens, the suffix will be ane, so we would call this pentane. But this is not just regular pentane, this is a special type of pentane. Specifically, it's the pentane that has this extra methyl group on. So we go on to step number 2, number the chain so the first substituent is at the lowest number. Well, if I count from left to right, 1, 2, 3, 4, 5, it puts a substituent at position 4. However, if I count right to left, 1, 2, 3, 4, 5, it puts a substituent at position 2. That's a lower number than 4, and so the correct name and location would be 2-methyl. Name the groups attached and specify. At the 2 position, we have a methyl, and so our final name is 2-methylpentane. The meth says what the substituent is, so it's the identity of the substituent. Okay. The ol, the YL, says that it is a substituent of something else, I'll say of the parent. Right. The pent is the base name of the parent, and the ane means it's an alkane, meaning only carbons and hydrogens are allowed. The 2 says where the methyl comes from, I'll say location of the substituent. And the hyphen separates letters from numbers. So every part of the name has meaning, and it's very specific, and there's no redundancy. That's a nice simple one. Let's do something that's a little bit more complex. Okay, so in class I gave the same example. So pause the video right now and try and come up with the name. If I count 1, 2, 3, 4, 5, 6, 7, 8, 9, I get 9. If I get 1, 2, 3, 4, no. 1, 2, 3, 4, 5, 6, 7, 8, no. 1, 2, 3, 4, 5, 6, 7. So the best way to count would be either 1, 2, 3, 4, 5, 6, 7, 8, 9, or 1, 2, 3, 4, 5, 6, 7, 8, 9. If I count from right to left, I get a substituent at 1, 2, 3, 4. If I count from right to left, from left to right, I count 1, 2, 3. 3 is less than 4, so the proper way is to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Get in the habit of writing numbers next to your carbons. It'll make your life so much easier. Just do it. Okay, so now that I've found the longest chain, I've numbered it accordingly. Now I have to say a 9 carbon long chain. What's the prefix? Known. What are we talking about? I'm going to need to generate a little bit of space, so I'm just going to move this real quick. What type of functional group are we talking about? We're talking about an alkane still, so we drop the E and add ane. Okay. What do we have attached? At the 6th position, what is a group that has 2 carbons called? It's called ethyl, so we have a 6-ethyl. And I'm just floating it here for now. I'm just writing the puzzle pieces down. I'll put them together in order later. At the 3 position, what do we have? A 1 carbon unit. That's called a methyl. We have a 3-methyl. And that's all of them. Now we have to put it together alphabetically in the name. What comes first? E or M in the alphabet. Hopefully you watch Sesame Street. You know 6-ethyl hyphen 3 hyphen methyl nonane. Okay, so that's done. Remember, hyphens separate letters from numbers, commas separate numbers from numbers. So I'll give you one more example, and then same example from lecture, and then I'm going to move on to conformations. So we got this guy, doot, 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 and doot, 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 doot. Okay. Pause the video and try and name that real quick. Where do you count from? You count the longest chain. If you count left to right, you get 1, 2, 3, 4, 5, 6, 7. Nope. 1, 2, 3, 4, 5. Nope. 1, 2, 3, 4, 5. Nope. 1, 2, 3, 4, 5, 6. Nope. 1, 2, 3, 4. No. What if we start down here? 1, 2, 3, 4, 5, 6, 7, 8. That is correct. So do we count from left to right or right to left? 1, 2, 3 versus 1, 2. 2 is less than 3, so we should count 1, 2, 3, 4, 5, 6, 7, 8. We found the longest chain. We've numbered it accordingly. What do we have? At the 2 position, what do we have? We have a methyl group, but it's happening twice. So we have a 2-methyl, and we have another 2-methyl. I'm just going to write it down explicitly for now, and I'll combine them later. At the 3 position, we also have a methyl. So we have a 3-methyl. And at the 6th position, we also have a methyl. So we have a 6-methyl. Right? What do we have at the 4th position? Well, technically we have a 1-methyl ethyl, but a way to recall this whole group as one thing is called an isopropyl. Oops, I-S-O-P-R-O-P-Y-L. Okay. This group collectively is called isopropyl. It's kind of a slang name that's been grandfathered in as IUPAC acceptable. By the way, that's the name of this system. It's called the IUPAC system. It's the official formal name, International Union of Pure and Applied Chemistry. Okay, so it's the IUPAC name. So we just build a name the same way we did before. Parent chain, oct, because it's an alkane, it's only carbons and hydrogens, it's octane. But now we don't want to say 2-methyl, 2-methyl, 3-methyl, 6-methyl, 4-isopropyl octane, right? That's a lot of words. So we can condense all of these together into the same thing, and because all of the methyls are the same as each other, right? A methyl is a methyl is a methyl, we say, where am I at here? We say 2, 2, 3, 6, which means at 2 and at 2 and at 3 and at 6. What do we have? We have 4, that's tetra. And what do we have? We have methyls. So it's 2, 2, 3, 6 tetramethyl octane. Right? That takes care of all our methyl groups. And what do we have left? We also have an isopropyl, 4-isopropyl hyphen 2, 2, 3, 6 tetramethyl. So now I have a question for you, or I have a comment I need to make. When we're talking about the alphabetization, how come the name is 4-isopropyl 2, 2, 3, 6 tetramethyl octane instead of 2236 tetramethyl 4-isopropyl octane. How come I don't switch this with this? And the reason is we're doing alphabetization. I for isopropyl, M for methyl. This doesn't count for alphabetization. Alphabetization doesn't count for alpha. Right? So you talk about the identity of the group. So I comes before M, and so it should go first. It also comes before T, so it's not a perfect example. But I comes before M, that's the comparison that you want to make. Right? If it was tetraethyl, right? So if I had ethyl groups instead of methyls, now ethyl comes before propyl, right? A-E-I, right? Yeah. So tetraethyl would go first, and the name would then be switched. Okay. All right. So there's plenty of homework examples for that. I should be able to give you guys a structure, and you give me the name, and then I give you the name, and you give me the structure, right? So if I gave you, like I did in lecture, 3-ethyl 4-methyl hexane, you should be able to draw that. Pause the video, try and do it right now. All right, conformations. A conformation is just an orientation in space, right? So I'm unfortunately giving a video right now. I'm not standing in front of you. This is one conformation of little man. This is another conformation of little man. He doesn't mind that, right? This is another conformation of little man. He's not particularly happy. His legs are bent backwards. Maybe he's jumping, right? And this is the sad version of little man, or maybe he's examining an ant on the ground. Okay, conformation is just an orientation in space. So if I were to draw ethane, right, we draw the Lewis structure like it's flat. We know it's not flat. Who are we kidding, right? It's not really flat. Really, ethane has three-dimensionality to it, where two of the hydrogens are flat. We have a wedge that says this hydrogen's coming out at us, this hydrogen's going back. This hydrogen's coming out at us. This hydrogen's going back. And I try to trick you by drawing the hydrogen really small, like the letter H a little bit smaller, so it looks like it's far away, right? Perspective drawing. All right, so what this says is that this is one conformation of ethane. But what I could do is I can take this sigma bond, this sp3-sp3 hybrid overlap, and I can rotate it such that one carbon stays the exact same, does not change its orientation in space, but the other carbon does. And so now I'll get one hydrogen coming out at us up on the top, the other hydrogen coming back, and the other one like that, right? This is called the sawhorse position. Sawhorse. H-O-R-S-E. Okay, it's a common position for the conformation of ethane. If I say, okay, I'm going to turn into the little man, and I'm going to walk him down here, and I'm going to have him look at the molecule now down this angle. So yeah, if he sees a carbon, and then a carbon that is occluded by the front carbon, what would he see? He would see something that looks like this. I draw a circle just to represent what he sees. Carbon in the middle. Up on top, relative to his position, is a hydrogen. Down and to his right, right? He's standing here, so down and to his right would be a hydrogen, and down and to his left would be a hydrogen. What about the carbon in the back? Well, the carbon in the back, up and to the right has a hydrogen, up and to the left has a hydrogen, and straight down has a hydrogen, so we would see something like this. This method of drawing a three-dimensional object in two-dimensional space is called the Newman projection. Okay, it's very important. Right? So basically, the ability to take a two-dimensional flat drawing, convert it to a three-dimensional flat drawing, and then reconvert it back to a two-dimensional drawing is called projecting, and this specific type of projecting is called the Newman projection, and it will help you understand the chemistry later on. Okay. In this particular position, the bond angle between these guys is 60 degrees. They're relatively far apart, and specifically we call this the staggered position. Is it ER? Yes, ER-ED, staggered, meaning the groups are far away from each other. If I just rotate this bond a little bit, I'm spinning one carbon relative to the other, and if you have a model kit, that would be a great thing to do right now. And you can get something that looks like this. The front carbon will remain the same, and we'll spin the back carbon such that the three hydrogens overlap each other. Because they overlap each other, they somewhat bump into each other in three-dimensional space, or at least they have a potential to do so. And then the energy of that conformation, right, a conformation in orientation space, the energy of that conformation will go up. We call this the eclipsed conformation. Molecules don't like to be eclipsed if they can get away with it. Okay. In the simple case, where we're just talking about hydrogens, not a huge deal. The difference between the staggered and the eclipsed conformation, I want to say, is only a couple kilojoules. Don't quote me, I don't have it looked up, but I think it's a relatively small amount. It does become a bigger deal, however, when you start dealing with molecules like this. Butane. So what I'm going to do is I'm going to draw butane, and I'm going to draw it as the eclipsed first. And what I want you guys to do is pause the video and draw the Newman projection for butane right now. Okay. Hopefully you got this. This is the carbon in the front. It actually doesn't even matter which side you look at it from this time. And then we have a methyl right here, hydrogen, and a hydrogen. And if you notice, I always draw my little line slightly to the right of the one that's in the front, slightly to the right, or I shouldn't say right, slightly to the clockwise, slightly to the clockwise, slightly to the clockwise. Just for consistency's sake, it makes it a little bit easier to understand. If you draw this one here, like this, if you were to draw it like that, that wouldn't be wrong, but it's a little misleading because it makes it look like this bond angle between this hydrogen and this methyl is different than this bond angle, right? It's a little bit smaller. So, like I said, it's not wrong, but it's just a bad habit to get into. So just try and always draw it to the same side, either always to the clockwise or always to the counterclockwise, just for consistency. It'll help make things easier to understand. All right, now you have methyl groups banging into each other, right? Essentially, this methyl group interacts in three-dimensional orientation here, and this interaction is bad. That interaction is called steric strain, or sometimes it's also referred to as steric hindrance, H-I-N-D-R-A-N-C-E, right? They're physically hindering each other in space. They're bumping into each other, okay? That's a bad thing. It makes the energy of that conformation go up. So if bumping into each other is the worst possible combination, what would be the best possible combination? Can you draw the Newman projection? That's ugly as hell. Can you draw the Newman projection such that you get the lowest energy conformation? Pause the video now and give it a chance. Hopefully you got something like this. If you did, I think you understand this and it's the right idea. You want it to be staggered, just like we talked about before. But you want the biggest groups, which in this case are the methyl groups, to be as far away from each other in three-dimensional space as they can. So that would be, if I were to draw it on paper, like this. Right? This methyl group is far away from this methyl group. If you have a model kit, go ahead and make this structure. Go ahead and make this structure, and just note how close in space these methyl groups are to each other. They're not touching each other just yet because the bond angles kind of point them away from each other, but they're damn close compared to this one. That's the only thing I want to mention about that. So if we graph the energy as a function of bond angle, right, as we rotate from the worst possible position, eclipsed, where the two methyl groups are right here. Oops, I put those in the wrong position. Right. Where the methyl groups are on top of each other, we're at the highest energy, and we go to the best position, where the two methyl groups are opposite each other. Right. We get something that looks like this. Man, I don't know why my pen is like jerking like that. It's not me. It's the machine. I swear. I don't have Parkinson's. Right, and it'll be symmetrical, and like that. So this would be 0 degrees, meaning the starting position, and this would be 180. Seriously? 180 degrees. I'm going to kill this machine. I'm literally going to punch it. It's not mine though, so I don't care. Alright, anyway. and that would be 360, where we're back to where we started from. Right, so this would be 60-degree rotation, so it's staggered but not perfect. And this would be 120, back to eclipsed, but the two biggest groups are not eclipsing, so it's not as high energy. You don't ever have to memorize these numbers, but just to give you an idea of how much we're talking about, this is about 3.8 kilojoules, and this one is about 21 kilojoules. This is a very measurable amount, right? So if the molecules got to choose their conformation, which often they do, they're always jiggling around in space. They always try to find the lowest energy conformer. That's what we call this. Most of the molecules will exist like this at any given time, right? I can't give you a percentage, obviously, because we don't do calculations here, but essentially, some of them will be eclipsed, some of them will be staggered, and they'll constantly be zipping through all these conformations, with the highest population being in this orientation in space. Okay, so that's all I'm going to say about conformations for now. I just want to quickly move to cyclohexanes, which is where we left off on Wednesday. I draw a cyclohexane like that. To name cyclo compounds, by the way, you just say, well, how big is the ring? 1, 2, 3, 4, 5, 6 carbons. That will be hex. It's all carbons and hydrogens, so that would be ane. But it's in a ring structure, so I attach the prefix cyclo. Right, so cyclohexane would look like this. If I had a substituent attached, like that, then I say, well, what do I have? At the 1 position, I have a methyl, so I have 1 methyl cyclohexane. If I had another thing attached, I would say, oh, at the 3 position, I have an ethyl. So that would be my, actually I'd have to rename that, so it would be 1 ethyl, this one would be the 1, and then this one would be the 3. 1 ethyl, 3 methyl, cyclo, you just stick that word in there, and then however big the ring is, cyclohexane. Anyway, cyclohexanes are not flat, right? This bond angle, ideally sp3 hybridized carbon, should be 109.5 degrees, but if it was a flat structure, it would not be 109.5. And so cyclohexane actually exists in 2 forms, chairs and boats. Okay. If you make a cyclohexane with your model kit, which you should be doing if you have not done so already, you'll notice that you can do this. If I take this carbon and I fold it up, I get the boat structure. And if I take this carbon and I fold it down, I get another chair structure that looks like that. We can go directly from chair to chair. We call that a chair flip. So let me label this real quick. That's a boat. This is a chair, right? By taking one up and one down at the same time, and that has a direct impact on what happens to the groups that are attached. All right, so let me make another one. Yes. So suppose I had a cyclohexane with a methyl group, 1 methyl cyclohexane, and I said, let's draw the chair or the boat. So we'll draw a chair, and if you notice, some of the carbons tend to point up. So this carbon points up, this carbon points up, this carbon points up, this carbon points down, this carbon points down, this carbon points down, right? These are what we call the axial positions, like a north-south axis. In that same structure, we also have positions that point away from the ring. So let's see, we got that one, that one, that one, that one, that one, and that one. This one's a little bit unclear. Okay, these positions are called the equatorial positions, okay, because they point away from the plane. So if you imagine all the carbons to be kind of like an equator, like if it was like a little sphere or a globe, the axial ones point directly up and down, the equatorial point out from the middle. Okay. It turns out that whenever you have something attached to a cyclohexane, you want to put the groups that are attached in the equatorial position if possible. So if I was going to draw the methyl group at the 1 position, I could draw it here, or I could draw it here. The lower energy conformer, these are both conformations in space, would be the one with the methyl group here. Okay. If I do a chair flip, where I take this carbon and I bend it up, and I take this carbon and I bend it down, now my chair would look like this, and my previously equatorial carbon will now occupy the axial position. And if you don't believe me, pause the video and do it right now. It's good practice. Because this is an axial position, and this is an axial position, and this is an axial position, what happens is, even if these are hydrogens, that methyl group will smash into those hydrogens because the molecules are constantly vibrating and bending and twisting around in space, and that will interact with each other and form what we call a steric strain, and specifically it will cause a 1,3 diaxial, right, axial interaction, and that 1,3 diaxial interaction will actually raise the energy of that conformer so that it doesn't want to do that, right? So if the cyclohexane, or in this case the 1-methylcyclohexane, got to choose which conformer, which conformation in space it got to occupy, it'll by and large choose that one. It's much lower in energy because the methyl group is out here. There's nothing it can bang into. Up here, it smashes into these two axial positions, so that's bad. Well, what about the boat? If I had the boat, I'm on a boat, and I put a methyl group here, unfortunately, there's also something on this side. So when you make the boat, you'll notice that you have this interaction now, right? This is called a 1,4 diaxial interaction. You notice all the diaxial interactions are bad. And that's also bad. In fact, it's even worse than the 1,3 diaxial, because if you build the boat and you put another methyl group here, they can actually occupy the exact same space, and that's terrible. All right, so the boat conformation is even higher in energy than the chair conformation, and we can play the same game we can with the Newman projections, and we can graph energy as a function of shape. If we start out with one chair, okay, and we do the other chair, so in the process of a chair flip, we end up with the lowest possible energy. In the middle, we have our boat, and then up here at the highest energy, we have this weird kind of half boat looking structure. It's like bent in between, right? As you're going from the chair to the boat, right, you have to go through this higher energy molecule, which the bond angles are not optimal for an sp3 hybridized carbon, right? They're not 109.5, and so that strains the molecule a little bit. Okay, so what we're going to do next time, I'm going to stop here. What we're going to do next time is we're going to consider what happens if you have more than one group attached. What if I have two methyls? Now I have to specify where they're at. Are they axial? Are they equatorial? Are they one axial and one equatorial? What if I had one that was here, but the other one was here? Or what if I had something that was one here, and then I had an ethyl group that was here, but I also had a methyl group was here, right? What is the impact of all these other groups on the ideal conformation of the cyclohexane? Right? So that's what we'll talk about next time. That'll end up chapter 3 for us. Then we'll start talking about chapter 4, chemical reactions, mechanisms, kinetics. We'll actually start doing some chemistry. Woohoo! And then we got our test coming up. So I believe I said chapter 3 homework is due next Wednesday, which is, let me pull up the date, Wednesday the 5th. But honestly, what I recommend is you do chapter 3 homework this weekend, all the stuff we just talked about. Try and get it done by Monday so that when we get to chapter 4 on Monday the 3rd, then you have a couple days to do it. You have the 3rd and the 4th to do it, so that lecture on the 5th you can ask me questions, we can do stuff, and then the time on the 6th, 7th, 8th, and 9th you have just studying, right? So ideally you want to have all your homework done, have some time to come to me with questions, or go to Adam, go to the Tutor Center, or whatever, get your questions answered, and then you're studying. Then you're reviewing, you're redoing homework problems, you're doing the recommended problems. I haven't made up my mind yet, but I might provide you a sample exam. I don't like to do that because of various reasons, but I'm considering it. But studying should not be doing homework problems. Doing homework problems is what allows you to study, right? So that's how you want to be structuring for this. First exam's not too difficult, so you might be able to get by with a strong Gen Chem understanding, but you definitely want to understand this conformation stuff, the Newman projections, because it has a big impact on chapter 5, chapter 6, chapter 7, and everything you're going to do from here on out. So have a good weekend, guys. Get your studying done, and then you have a little time to relax, and I'll see you on Monday. Good luck.